Welcome. Now we are going to start on our main topic for differentiation in terms of calculation, which is how do we calculate the derivative efficiently. So now we are thinking of derivative as a function, and we are looking at the process instead of starting with the function f and calculating the function which is the derivative of f. So we think of finding the derivative as a process, and this is called differentiation. So differentiation is a function on functions. It takes a function as an input, produces the derivative as the output. Sometimes these are called operators. We are not going to do very many of them, just two. So I won't introduce additional notation. But it's important to think of differentiation as something we do to functions. And it's emphasized by a notation that I will often use. I will denote the derivative sometimes as d by dx of something. So here, instead of thinking of the derivative df over dx as the limit of fractions, I'm thinking of it as something I do to the function f, and d by dx tells me that what I'm doing is differentiation. Now, elementary functions, the kind of functions we most often deal with, are built up from a small number of building blocks, essentially just powers and exponentials, using the basic operations on functions, 4 arithmetical operations, composition, and inverses. So if I know how to differentiate basic building blocks, and I know how to differentiate combinations of functions in terms of derivatives of the building blocks, then I can differentiate any elementary function. Of course, what I'm really doing in that case is taking an expression that defines my function and producing an expression that will give me the derivative. But as we usually don't distinguish between functions and the expressions that define them, we won't distinguish between the two different processes either. So now let's look at some of the basic rules. There are some rules which deal with combinations of functions. One such for differentiation says that differentiation distributes over addition and subtraction. That is to say, if f and g are differentiable, then derivative of f plus g is the derivative of f plus the derivative of g. Derivative of f minus g is the derivative of f minus the derivative of g. It turns out multiplication and division are more complicated. We will get to that later. Very often when we calculate operators on functions, it turns out multiplying a function by a number is simpler and has better properties than multiplication in general. So it's customary to separate out multiplication by a number, by a constant function, from multiplication by arbitrary functions. And the same is true of differentiation. The rule for differentiating a number times a function just says that multiplying by a number and differentiation can be interchanged. That's to say, if you multiply by a function by a number and then differentiate, you will get the same result as first differentiating, then multiplying by that number. In symbols, d by dx of k times f equals k times df over dx. Note that these rules require that you know some derivatives before you can use them. So in order to feed into these rules, we need to have derivatives of specific functions. The simplest such rule is the power rule, which tells me how to differentiate power functions. That is, functions of the form x goes to x power n, where the exponent n is a number, a constant. We have done some examples of this. While talking about calculating derivatives from definition, we differentiated x squared, which is the derivative of x squared, and we saw that it was 2x. And we also did derivative of 1 over x, which is x power negative 1. We got negative 1 x power negative 2. And while talking about limits, We did a derivative, even though at that time we didn't know that's what the problem was about. But if you remember the other way of doing difference quotients, this limit is just the limit of difference quotient for square root of x, which is x power 1/2. And we get 1/2 times x to the power negative 1/2, even though we didn't write it that way. And these are all special cases of this power rule, which tells me that derivative of x power n is n times x to the power n minus 1. Now 1 and x are also power functions, but it's convenient to have separate rules for them. And again, we have done this. We know the derivative of any constant function, not just 1, is in fact 0, which will be the case where of n equals 0 in the power rule. And derivative of x with respect to itself is 1. And that's the case n equals 1 of the power rule. We won't worry too much about proving the power rule, especially for arbitrary exponents, even though it's always true for any constant exponent. Next time, we will look at how we can use the power rule to differentiate polynomials and somewhat slightly more general functions. I will stop